So let's see some more realistic cases of the Poisson ratio. So if we get a Poisson ratio of about 0.25, which is a realistic Poisson ratio, let's say this is 0.5, you will see that the coefficient A for alpha equal to 1, I have already made these numbers, is going to be about 2/3. And if you have a bigger Poisson ratio, this one is going to decrease. So the bigger the Poisson ratio, the smaller the coefficient A, and also the larger the Biot coefficient, also the larger the coefficient A. This is 0.35, yes, that's 0.35. So I just want to plot the variation of A as a function of Poisson ratio and alpha. We know that, as we saw in the results of Biot coefficient, at least for sandstone, that as we go to the left, that means a tighter rock. Okay, so yes?
So if nu is equal to 0.5, then A is 0?
If nu is going to be equal to 0.5, so this one is going to be 0, right? So yeah, you will end up with a line over here where there is no change in total stress.
Then it would be a fluid because absolutely there's no volumetric change.
So there's no volumetric change, and all the load, all the effective stress is going to the sides as you change the effective vertical stress. So these plots are very useful, and they allow you to see what is the evolution of total stresses as a function of pore pressure, but total stress is not really the right parameter to plot in terms of rock failure. So instead of that, let's try to see what is the equivalent of this plot, but in terms of effective stresses. If you do that, you can find that the stress path of a reservoir subjected to depletion is going to be, this is normal stress, this is shear stress. At some point, you have your initial effective horizontal stress, and this is your vertical effective stress. As you decrease the pore pressure, how much do you think the effective vertical stress is going to increase? So I'm looking at this point over here. How much is this one going to increase? The change in pore pressure, close, but not exactly on the value. Times alpha, right? Because we now have modified slightly a little bit our effective stress equation. If you change a magnitude delta P, the pressure, and in this case we're reducing pressure, if we reduce the pressure, the vertical stress is going to increase by an amount alpha delta pp. And if you change the pore pressure, imagine that now we have here S22 minus alpha pp, so there will be minus alpha pp here. If we take the derivative of that with respect to pressure, that will be A minus 1, right? So because there is going to be an alpha pp over here too. So if we decrease the pore pressure, the horizontal stress is going to increase an amount which is lower than this. And how much lower? That will be determined by the coefficient A. But it's going to be less than that. As a result, before I write that change, I hope that you notice that now we have more mean stress. Both effective stresses have increased, and we have a bigger Moore circle, and the Moore circle has also moved to the right. So this amount over here is going to be 1 minus A delta P in absolute value. And if I were to plot the stress path, I could continue, drawing more circles, but I don't want to draw too many circles in here. Something that you can do instead of that is just to draw the stress path of the top of the circle, and it will be a line that will move in that direction with a slope that if this is 1, this is going to be 1 minus 2 times the Poisson ratio. So let's come back to the sensitivity analysis on the Poisson ratio. If your Poisson ratio, let's say it's 0.1, very little expansion to the sides, you will see that your Moore circle is going to increase very quickly in diameter. So 1 minus 2 nu is going to be 0.8, right? If you have a rock in which you have a large Poisson ratio, let's say 0.3, that amount is going to be 0.4, much less, and this one is going to be 0.6. So the bigger the Poisson ratio, the more, the less steep this path is going to be. If you have a very small Poisson ratio, that could mean that, let's imagine that that you had a shear failure delimited by that line. If you have a small Poisson ratio, your stress path is going to go like this, and it's going to run into the shear failure. If you have a large Poisson ratio, it's going to go mostly in this direction. And I don't want to draw the line over here because it would be too many lines in the Moore circle. But instead, let's draw this stress path as it is more conventionally done, instead of in Moore circles, in terms of the effective mean stress, which is a function, if you remember, of I1, as actually is the first invariant divided by 3 of the effective stress tensor, and here as a function of Q, which is a function of J2. This one quantifies shear stress, this one quantifies mean effective stress. If we start at some point over here, similar as we saw before, let me see what colors I used. I used these ones. So somewhere over here, we're going to have our shear failure limit, and somewhere over here, we're going to have our compaction yield limit. And the stress path with depletion, this is for delta P less than 0. It may go into the compaction yield, or it may go into shear failure and continue in that direction. So now with these equations, we know we can calculate how much effective stress is going to increase and how much total horizontal stress is going to decrease. Knowing how much effective stress increase is going to let us know if we know what kind of material we have, if we go into crashing, or if you go into shear failure. Crashing most times is not going to be good because if you crash grains, if you crash the rock, permeability is going to go down, It could be beneficial from the point of view that as you crash the rock, pores that were big are going to get smaller, and the crashed particles are going to occupy those large pore spaces, and they may help drive more fluids out of the formation, like squeezing a sponge, right? That's something called compaction drive. So it may be good sometimes. What do you think about shear failure? It's going to be good, it's going to be bad. What do you think? Bad? Why? Why would it be bad?
Craft means there's craft just created, and that creates high contrast in Biot DTP, and that basically doesn't do very well for reasons.
I think you're correct. I think you're correct, but it really depends also on the kind of rock that you're dealing with. For example, if you had a reservoir made out of sand, and if you had lots of shear failure, especially at a very high confined stress, that will create something which are called shear bands, in which the shear bands have a lower permeability than the sand itself. However, there are some type of reservoirs that have natural fractures in it, and this is mostly the category of unconventional formations, that by creating this shearing into the formation, you can get those fractures to move respect to each other, and as they move, they will dilate as well, and as they dilate, they will have more permeability. So they will actually help you to increase permeability. There is a limit for that, though. You want to say something?
But I think his point was that as you increase permeability, you actually increase heterogeneity as well. That's gonna decrease the efficiency of any flooding you want to do.
Yeah, if you're doing flooding, right? But if you're not doing flooding, if you're just depleting, I think it would be slightly different.
Yeah, probably if the fracture acts as a main pore in the reservoir.
Yes.
Fracture helps.
Yes. But yeah, well, if you're doing flooding, yeah, probably that may not be good because you're going to break through very easily through the formation. But there are some cases in which fractures can help you. Shear fractures can help you to increase permeability. But some other times, if you have too much of this fracturing, like for example, over here, probably as you get to here, you have a rock over here, you create some fractures which help some of the fluids in the matrix to move to the fractures and move closer to the formation. If you continue too much on this path, you're going to create a lot of fracture slip. And that fracture slip is going to grind the surfaces of the fractures, and it's going to create small fines that then are going to get clogged into the fractures, are going to get clogged near the wellbore, are going to get clogged into pumps that you may be using for producing fluids, and that's not good. Actually, now in unconventionals, especially in late stages of production where the pore pressure is very low, they're starting to have these kind of problems of formations of fines. Okay, so there's one more thing I want to talk about, this drain problem or reservoir depletion. And the problem is, so we have calculated how much the stress will change in this direction. Now I would like to calculate how much the surface is going to deform. And this is what is called on surface subsidence. How can I get that number? I want a displacement, okay?
So you take the strain
Okay.
and then do free direction and you work backwards from the kinematic equation to get the displacement.
And that would be? Okay? So, and simply, that delta H is just going to be the height of the reservoir times epsilon 33. So, we'll like to compute what is epsilon 33. And for that, it's not too complicated, okay? But I think that I like to spend time in some other things. Basically, what you do is you take equation 2 and you replace S22 from here into there, and you will find that epsilon 33 is going to be equal that to this amount. Do you recognize this guy?
It's not on the screen right now.
Okay, so you cannot recognize it, I guess. So now, over there. We already computed that one before, and we call this one the constraint modulus. And from here, I can also obtain that the variation in deformation in vertical direction as I deplete with pore pressure varying and no change in overburden stress is going to be equal simply to alpha divided by m. So that's how you obtain what is the strain. And if I were to make this simpler, so delta epsilon will be equal to minus alpha over m delta pp. Is that a compression or a contraction? I'm sorry, a contraction or a dilation? Contraction, right? Notice that, sorry about that, notice that this is negative. So negative and negative, that will give you positive, that will give you a compression. So how much subsidence then you get is going to be proportional to the thickness of the reservoir, initial thickness of the reservoir, times this part. Coefficient, Biot coefficient is going to play a part, but not too much. But this is basically how stiff the rock is, and it's also going to be proportional to the change in pore pressure. I'm assuming in this very simple model that the subsidence is going to be the same in here than over there, which is not exactly true, right? But if it's shallow, it's going to be very close. It's going to be very close to that value. All right. Any questions about this problem? This is exactly what you have to do in your CMG assignment and your depletion assignment. And you will have to compare and the analytical solution with the numerical solution and draw the stress paths for depletion in the case I gave you. So if you need help with CMG, please email Jeffrey. Jeffrey knows how to do it. Charlie knows how to do it too. So you can contact them. And if you need to use the software, well, okay, you have to use the software, right? But if you don't have it installed in your computer, some of you do have it installed in your computer, you can come here to the laboratory. So it's right here. And you may not log in if you're not in this department, but you send an email to John Cassibury, and he's going to allow you to log in in these computers. Okay, you may copy me if you want in that email, so he's aware of that. All right, that was an example of a drain problem. Now we'll get into an undrained problem of poroelasticity. And here we're going to derive a few equations, but it's not going to be too long. Don't worry. So we drain loading, we said that we allow the fluid to come out from the pore space so that there is no increment in pore pressure due to the deformation of the porous solid. With undrained loading, there is no fluid that comes in or out from the pore space. This is mostly a theoretical condition because many times it's almost impossible to maintain a perfect undrained loading. And we'll discuss that a little bit later, but theoretically you could do something like that. It's going to be useful to derive some parameters. What is the amount? If I told you, tell me how much mass per unit volume I have inside a porous medium, how much is that going to be?
It's 1 minus the porosity times
No, I want fluid mass. Porosity times fluid density. That's it. So the amount of fluid,
times the volume
no, but this is per unit volume.
per unit volume.
So if it's per unit volume, then we just need porosity. So porosity per volume divided total volume. So per unit of total volume, this is going to be the amount of fluid that we have in a porous medium. So what we like to do here is to analyze what can be the variations of that amount of mass of fluid within a porous medium. So I could use the rules of derivatives and separate this term into variations of porosity, and also porosity can vary, right? But also density can vary. We're not assuming in this case an incompressible fluid. The density of the fluid can vary. If your density varies because you increase the pore pressure, you're going to have more fluid in it. I'm going to manipulate this equation for the purpose and for the equations where I want to get. And in order to do that, I'm going to divide by density of the fluid. So here I'm just going to have that term, and here I'm going to have this term with the variation of fluid density divided fluid density. Do you remember how we call, what is the variation of porosity? We call it this var phi, a Greek letter. And we had an equation for that. From poroelasticity, this was equal to the Biot coefficient times the volumetric bulk strain plus the variation of pressure plus pressure divided the pore modulus, right? So if I replace this in here, but notice that again we have a derivative, right? So this guy, it will be that guy, but if I take the derivatives, this will be alpha variation of volumetric strain plus 1 over n variation of pressure. And this one over here, I'm going to use the definition of fluid compressibility. The definition of fluid compressibility is that a variation of fluid density is equal to the, I'm going to write it in terms of the bulk modulus of the fluid times pressure. So the higher the bulk fluid density, the smaller the variation of fluid density with a given change in pore pressure. And I'm going to work as it's done in the derivation in the book from Cousy in terms of bulk modulus of the fluid, but you should remember that the compressibility of the fluid is the inverse of the bulk modulus of the fluid. It's the same thing, okay? So let's see. We have variation of density. Here we have density. So if I move this density over here, I'm going to have porosity times 1 over kf times dp. Let me write that again. So those are the two terms that I had before. And notice that now I have two dp's, right? So let me write this again. So I'm just going to group these two. And now I have an equation of the variation of fluid mass divided by the density as a function of the volumetric strain of the porous solid and the variation of pore pressure in the porous medium. I'm going to do one more thing here, which requires an assumption. I'm going to assume that I have very small strains. If I have small strains, this parameter that it's really a variable, is not a constant. If I have small strains, I can assume that the initial porosity is more or less similar than the porosity at any time, but the changes in porosity are much smaller than the initial porosity. If I do that, now this is a constant. And that constant is called the Beot Modulus, which is a constant. It's a constant, or it's a coefficient, as you may want to call it. Remember that n, we knew what n was. N, let me write it somewhere over here. N is equal to this amount. So as soon as we know alpha, we know the porosity, we know the compressibility of the solid, we know the compressibility of the fluid, we know what the Beot modulus is. But now the Beot modulus has the two components: compressibility of the fluid, compressibility of the solid. And why? Because if you want to compress a porous medium filled with a fluid, and if you're not letting the fluid escape, you must consider what is the compressibility of the fluid. It's not the same compressing a porous medium filled with gas than a porous medium filled with water, fully saturated. It's not going to be the same. It's going to be stiffer to compress the porous medium filled with water. Okay, so we're halfway to the equation that I want to write. Okay, let's see if we have time. I think we do. So we're going to couple now what we found here with the continuity equation. with the continuity equation with fluid flow, I know that the variation of fluid mass per unit volume as a function of time in a given representative elementary volume is going to depend on what gets in and out. And this is the divergence of the fluid flow. Basically, this term over here means that everything that gets in must get out, and if it doesn't get out, it has to be compensated by an increase of fluid or density or increase of porosity inside a porous medium. This is a very important equation, guys. So, do you all understand what these two terms are and how they are combined? Yes, John. You don't get it? Okay. So, this term tells you the variation of amount of fluid in a porous medium as a function of time. And this one over here, it tells you what is the variation of flows here and there. So for example, let's say that we inject 1 unit in this direction and you get 0.5 in this direction. Where is that fluid going on? Is getting into a black hole? Not very likely, right? Unless you are to a very high mass density point, but we'll not get into that. So if we assume no variation of density, no variation of porosity, if you're injecting 1 in this direction and you're getting 0.5, well, very likely here in this direction, if you were getting a 0.5, now you have to get 1. So whatever comes out of the porous solid, 1 and 1.5 has to be equal to whatever gets in. That is this term, is the variation of fluid amounts in different directions, where these are derivatives in a function as a function of space. And we could have a case which does not follow this one, but let's say that you're injecting 1.1 and you're getting 1 and 0.05 in a given amount of time. If the fluid is not coming out, that means that either the porosity increased, or if the porosity remains the same, that the density of the fluid increased. So that porous solid acts as a